Okay, so we are continuing with meshes. So in the morning, I said that mesh is structure that has embedding in a manifold, but it doesn't need for that embedding to be very nice. For instance, so a mesh is embedded in a manifold, combinatorial mesh. Embeddable in a manifold. But the result might not be a manifold itself, but the result may not be a manifold itself. And therefore, here's some examples. For example, this mesh here, a simple mesh, 1D mesh, cannot be embedded in manifold because this point has 3 edges around it, or if it has more. But a one-dimensional manifold should be like a curve, should not have 3 exits, but should go in a single direction. Some counterexample for a 2D mesh would be like that is not embeddable. So things like that. Oops. And now maybe something like that. Okay, maybe this should be seen, and this is not seen. Yeah, something like that. So here again, this edge here has so node with 3 edges and edge with 3 faces. Or more. So this is not a valid 2D manifold. And so I'm going to give, in one of the appendix of my 2020 paper, there are more examples. There are 3 conditions for something to be called manifold-like, but I would do only the first 2 because the third is a bit more involved, and I will not do it much, but let me do the definition of what is to be like a manifold. So everything's fine with the yeah, okay. So let M be a combinatorial mesh, and this is the dimension of M. And let me see how I framed it. Okay. And assume that M has the property. Let me mark it some way. So the property star. I don't have name for this, so I'll just make property star. The following property. So any any d-1 cell is included in one or two D cells. So here, this is not a one mesh because a zero cell has three edges, and this is not a two mesh because a one cell has three faces around it. So, and if it has, if a D minus one, if C a D minus one, if C a D minus one cell has, so two cases, is included in if it's included in a one D cell, it is a boundary. It is a boundary. Hyperface, maybe. Hyperface. And if it's included in a two D cells, it is an interior hyperface. But this also doesn't write well. Sorry? Okay. So let's give some examples. So okay, I will denote like red boundary and green interior. So in this mesh we have, these are the boundary, and these are interior. Now consider another mesh, 1D. So this mesh doesn't have any boundary, it doesn't have any boundary elements. All elements are interior. So continue. We started here. Okay. I'll just for people who came later continue from here. These are 1D, so this is 1D examples. So if it's closed, it doesn't have boundary, like in the 2D. So we have let's say this mesh here. and or maybe even here as well, some diagonal. So I write our boundary. So these are the boundary elements. And these are the interior. But if it's a boundary of a tetrahedron, for example, it's all boundary cells. So it's all interior cells. Sorry. So we have here, 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 and everything. The one facing me. And in 3D, a cube, it has, I'm not right, but usually what is, because you embed 3D usually in 3D, what you see as a boundary is usually boundary. But I want to show examples like here, everything is interior because this is a 1D mesh in 2D. Okay. If cube is in 4D, okay. Oh, yeah. This in n dimensions. Okay. There is one example here that I want to show. How is it? Something like that. Maybe it can be made simple. But here we don't have, so I'll just comment on it. I don't have this cell here, only the rest. So again, we have edges. This will be, for example, a boundary edge. Okay, let's write it. The boundary. So boundary goes like that. But also here as well. No. And this is also boundary. And this is also boundary. Because I don't have this cell here. And this is in here. Now in this example, because this is what I want to do next, maybe. This is some strange example because when I take the boundary, it will be one mesh, but it will not be very well behaved because it will have points with this point will have 3 edges around it. So if it, even if the initial one has is like a manifold in some sense, the boundary is not. But this is a detail that it's not worth to go into. Okay, so now let's define what a fundamental class is. I will need this for doing like some kind of discrete integration. So let M be a D mesh, combinatorial mesh. This is the dimension of M. And M has the property star, has the property star. We say that a relative, we say that a relative orientation epsilon is compatible if all interior cells, so for any interior cell, C in ND-1 with included in these cells A and B. They have opposite orientations. So epsilon AC is minus epsilon BC. So usually we have, for example, if I have such a, let's say, this mesh, and I'll take this here and this here, and so this is F0, F1, epsilon 0, for example. And I require that epsilon F0 of E0 is minus epsilon of F1 E0. This is what is required. And so on if you have more cells on the interior. So not all meshes have this property. If it's a mesh that so not all meshes have this property. If it's a mesh that is a partition of the Möbius strip, because it's not oriented, and this will not have such orientation. But we will assume that it has such. And so the fundamental class is then defined by the fundamental class of M. Some curved bracket, square brackets, and it is the sum of all these cells. So A in MD, A. This is a D chain. So this is C, D, M. So in this example, the fundamental class of M is F0 plus F1. And the good thing about the fundamental class is that if we take the boundary operator everything that is inside will cancel out, because we have with any cell here we have 1 plus and 1 minus from the two sides, and only the boundary will remain. So D of M contains only boundary terms. The interior cancel out. The interior one cancel out. Okay. And we can define discrete integration. So discrete integration of D-forms only, of D-forms. So if not D-form, D-cochains, sorry, D-cochains. If sigma is a D-cochain, then like integral of sigma is sigma applied at this. So to be in this example, sigma of f0 plus sigma of f1. So in the above example, sigma of f0 plus sigma of f1. Okay. I previously introduced the Rham map, which just takes integrals over cells and sums them. And the integral map, the Rham map can be described as a, so the integration can be described with this discrete one combination with the Rham map. So if X is a D-manifold, so M is embedded in, not interpreting, and okay, and M is embedded in X. We have, and omega is a D-form. Then the integral over X of omega is the same as integral over not only embedded, but okay, it's embedded in X by some function phi, by phi. So the integral over the whole set is the same as integrating the omega applied at M. So let this, for example, this here. Integral over, let's call this X, the embedding. Integral over X of omega is integral over F0 of omega plus integral F1 of omega. And this is the same as so this is RD omega over F0 plus F1. So from before, RD omega was defined, so RD omega is integral over F0 omega times F0 plus integral over F1 omega times F1. And when we apply this to the sum, we'll get these two terms. Because applying this to this, F0 with F up with 0 is 1, F up 0 with F down 1 is 0, so this term doesn't contribute. And then we have this with for mixed formulations. Okay, now we don't still have analog of the so okay in the morning I wrote some diagram with the Rham map and the boundary operators and co-boundary operator and discrete exterior derivative. And so the exterior derivative is represented by the co-boundary operator, but we don't still have representation of the wedge product, which is important in order to state the physical problems. So first, let's define what such kind of operation should do. So what we need is to have a very rich calculus in order to state physical laws. That is what we know. So let M be a combinatorial mesh. It has some boundary co-boundary operator. An operation this smile symbol from CPM times C plus 1 times CQ and to C P plus Q M. Here P and Q are integers. Is called, there some should be less than the dimension, otherwise it will be 0. It's called, okay, so P plus Q is less than T, dimension of M. Is called a cup product if it has the following property. So first, it is graded commutative. So sigma star, not star, sigma smile rho is minus 1 to the power of PQ rho smile sigma, where rho and sigma is a P cochain and rho is a Q cochain. 2. It satisfies the graded Leibniz rule. So delta, again, sigma with rho is delta sigma smile with rho plus minus 1 to the power of p sigma smile with delta rho. Again, the same thing here. So we have this here as well. Sigma rho as p form and q form. Okay. 3, it is local. In the sense that if C is a P plus Q form, so P plus Q cell, then sigma smile rho at this cell C is sum of some elements, so it is some A I'll call it A, not C. B is in A and C is in A and C is in A and B is MP and C is MQ. So we have some sum of some coefficient lambda ABC, and then sigma is applied to B and rho is applied to C first. So which means that if you apply a cup product at some cell, only cells on the boundary should have contributions, not outside. For some lambda ABC. So no contributions outside the boundary of A. Okay. Okay. And there is one more technical condition. For if one is the form in a C0 cochain, so one of Ni equals 1, or Ni and 0. So this is the one cochain that gives 0 at any node. Then one cup with sigma is equal to sigma cup with 1 equals to sigma. So cup products, this is what a cup product should have as properties. All the properties for 1, 2, and 4 are the same as for the wedge product and the exterior derivative. They are related with these properties here. This is the graded connectivity. We have graded Leibniz. We have the constant function 1 when multiplied wedge product with something is the something. And it's also local in other sense in the continuum, but yeah, it's local. If a cell, the wedge product only interacts with the closed boundary of at a point. Now, from what I know, wedge product can be defined on simplices, cubes, polygons, products of this kind of structures, and from cubes we can define it for quasi-cubes, which come naturally from one subdivision called Forman Subdivision, but I don't think I will have time to explain it. Andre, what do you think? To skip it, maybe.
I don't know. what I will find out.
So, I mean, I'm going to define a product on cubical, quasi-cubical complexes.
Okay.
Yeah, so we'll work with quasi, so from a mesh M, okay, so let me do a remark. From a mesh M, any kind in dimension less than 2, and with simple cells, so that means that in 3D, I will do any node in a polytope has exactly 3 edges in this polytope. That is in 3D. That means that we cannot have square pyramids. So a pyramid has 4 nodes, the vertex. So no vertices of square pyramids, for instance. So for any kind of this, simple cells, again, I to finish my sentence. In 3D, I have 3D 2 times, but anyway, we construct. Okay, the construction is generic, but for a construction called the Forman subdivision leads to a mesh, a quasi-cubical mesh. So a quasi i.e. all cells are topologically cubes, are topologically now this form of subdivision, it has some geometric meaning. The things called for discrete forms, but in 1D, it's defined cell by cell. So if we start with a cell, for example, 2 edges, then we split them in half. So we have the original edges, but then have new ones and connect them. Okay. In 2D, let's say we start with a pentagon, why not? I will not do it for the 3D example, but 2D. And so we have all the original nodes. But also for any one cell, we have a new node. And we have a node for the interior. And then we start connecting. First, we connect the one skeleton. I don't know, here I used different colors, but. And then we connect the center of the cell. It doesn't matter with the new nodes. And we have this here. So we started a pentagon, but we have 4 or 5 quadrilaterals. Okay. In 3D, if you have a tetrahedron, it goes to 4 quasi-cubes. So 3D tetrahedron goes to 4 quasi-cubes. And a cube goes to 8 cubes. So it's split in both directions, in 3 directions twice. In 2D, a square will go to 4 squares. In 3D, cube will go to 8 cubes. So to define on a quasi-cube, let's define topological orthogonality. So now I will use K. So usually M is the original complex and K is the Forman complex. So this is M, this is K. Let K be a quasi-cubical mesh. We have P and Q are integers. A is a P plus Q cell, so it is K P plus Q. B is a P cell, and C is a Q cell. We say that B and C are B is topologically orthogonal with respect to A. And I will write this as this, so B with C, sorry. Topological orthogonal to C with respect to A. I write this B, C is perpendicular, is in the perpendicularity of A. Is in the PQ perpendicular pairs of A. If B and if they are both subcells of A, if B, C are in subcells of A, and B intersection with C is a single node. So this is a single node. Now, I'll give a little bit more interesting example when we have a when we have a convex mesh. So let's call this. I don't know, I have this in my, but anyway, it doesn't matter. I'll have this example in the preprint. E0, E1, F0, F1. Let's call this E3, E2. Anyway, so, and let's call this, for example, N0. Now, N0 and E0 are perpendicular to E0. Their intersection is a single cell, the zero cell, and they are both subcells of E0. N0, E0, E1, not orthogonal. Because since their intersection is the empty set, N0 intersection E1 is the empty set. So this, okay. Again, okay, other trivial example will be N0 with F0 is perpendicular to F0, and we can have the other direction as well. It doesn't matter. So when one of the cells is a zero cell, it's trivial. It should be just a subcell of the other. Now let's consider one cell. So F E1, E0, E1 are orthogonal to F1. Let's call this N1. Because why? Since they are both, so since E0, E1 are subcells of F1 and E0 intersection with E2 is E1 is N1. And we also have E0, E1 is also, this is something interesting. It will not happen if we have straight cubes. It is topologically, this is 1, sorry. It's topologically perpendicular also to F0 for the same reason, because they are both cells of the same. Now, E0 and E1 and E2 are not topologically perpendicular. So E1 and E2 are not perpendicular. Since they have empty intersection. We can say that they are parallel. We can say they are parallel in F1. And before making a break, Let's give the straightforward 3D example. So this is V, this is E1. No, not E1. This is E0 and this is F0, for example. And this edge and this face have exactly this intersection. So E0, F0 is topologically perpendicular to 1, 2 of V. Because E0, F0 is N0. And they're both subcells. And E0, F0 are subcells of V0. So here, this is straightforward orthogonality. This face and this edge are, this is like X, Y, and this is Z direction. Okay, so let's make a break and I will define the product after the break.